Hello, let us continue with our lessons on our electromagnetic wave radiation and its properties. Today's lesson it's likely to be much more interesting, and let's go through the lesson where I'm going to cover some more properties and introduce you to the EM spectrum. Okay, we have been learning about the sky waves, ground reflected waves, etc., and its properties, and how it is able to bend due to attenuation and diffraction, etc., etc. Now we are just going to consolidate and see how the whole thing is affecting. Now, see the diagram. In actual, this is how it's going to happen. There is an aerial and a plane flying will receive some direct waves. That is right from the aerial, direct up to the plane, almost a line of sight. Of course, a little bit bending here, there. Of course, is there, but and also these ground waves at some point it is able to bend or it is able to get reflected, and that also reaches the plane or the receiver. So there are two paths in which the reflected wave is being received by the receiver. Okay, let's discuss this direct wave a little bit. The wave reaches the receiver in a straight line. Of course, while it is propagating, while it is traveling, it is losing its signal strength. That is what we call attenuation. So that follows an inverse square law. That means at half the distance, the signal strength will be 4 times. That means every time this thing doubles, the distance doubles, the signal strength will drop by 1/4 square of the distance it will drop. That's what we mean by inverse square law. And of course, it depends on the frequency. As the frequency increases, the wavelength reduces, and the water drops and gas molecules are attenuating the signal further. That means the water drops and gas molecules in the atmosphere, it further attenuates the signal, and this attenuation is more as the frequency is higher. Okay, which is the other one? This is a ground reflected waves. The ground reflected waves can be reflected by those objects whose size is more than half the wavelength. So yeah, when you study the wavelengths, of course, then you will be able to appreciate this better. Hindrance to efficient propagation uh, is due to the size of the reflecting surface, and useful in some applications such as weather radar, etc. That means that reflecting this property is because the size of for a weather radar you need very small objects. So the water droplet size is very small, and these weather radars incorporate very high frequency radars, so the wavelengths are small and they correspond to such sizes, so we are able to get better reflectivity from the atmosphere, water droplet, etc. So that's what the size of the reflecting object, how it affects the reflectivity. Now, as you notice, the receiver, that is the plane, is receiving the same signal which is transmitted at the same time from two different sources on two different paths. That is, one through the direct wave and one through the ground reflected wave. Now, there is an effect when these two come together, come at a point in time to the receiver, there is a effect. If they are in the same phase, they get added together, and it enhances the signal strength. Whereas at some points, if they are out of phase and they cancel out each other, then you get the signal strength fades away, or at some points you don't have a reception whatsoever. So this phase difference in turn depends on the angle of incidence, polarization of the incidence signal, and the conductivity of the reflecting signal. So all these factors put together give rise to some little bit of strange phenomena. Sometimes the signal strength is more, sometimes there is a blackout for a brief period. Could maybe there is a possibility that you are not receiving the signal. Yeah, like we always discussed, the we call this range to be line of sight, etc. But we know, we are learning that there are always phenomena in the atmosphere which causes bending and giving rise to a little bit of extra range, etc. There is a change in refractive index, and there is depending on the angle of incidence, there is a tendency for the ray to bend, and therefore it's not necessary that it is only purely line of sight. There is a little bit extra range which is it is able to get. In the earlier class, I taught you that this line of sight range from a transmitter is given by the formula d is equal to 1 decimal 05 into under root of height of the transmitter, that where d is in nautical miles and under root of the height, that is height is in feet. And I also covered that this doesn't give rise to longer ranges, and practically it's of no use if we are to get only these particular kind of ranges. But as we know, practically there are we are able to get much better ranges, and therefore experimentally we have been able to arrive at a formula d equals 1 decimal 25 under root of height of the transmitter plus 1 decimal 25 into height of the receiver, where d is in nautical miles and height again is in feet. This is the practically what you are going to receive in actual. Okay, as usual, let us take a numerical example and try to understand this particular formula which I covered. Let us take an airfield elevation at 900 feet, and there is a transmitter which is located at the airport and which is transmitting signal, say VHF transmission, and the aircraft is flying at flight level 400, that is 40,000 feet. And at what range, maximum range, can he expect to continue receiving the VHF signals? So, simple, straightforward application of the formula d equals 1 decimal 25 into height of the transmitter plus under root of height of the receiver. So, I kept the figures so that easy, so that you can work out easily. So 1 decimal 25 into under root of 900, that is the height of the transmitter, plus 1 decimal 25 into under root of 40,000 feet, that is so 1 decimal 25 into 30 plus 1 decimal 25 into 200, which is equals 1 decimal 25 into 230, which equals 287.5 nautical miles. That means when the aircraft is approaching from outside, the aircraft can expect to receive the first VHF reception at around 287 nautical miles. So that's what is the practical application of this formula. In our earlier class, we learned that the speed of the electromagnetic wave by and large remains constant, that is of the order of 3 into 10 to the power 8 meters per second, and a little bit variation, and as the frequency and the wavelength, how as to how they are correlated. Because the speed is velocity is constant, the frequency, when the frequency increases, the wavelength reduces, and vice versa. This is what we learned. Now let me introduce you to the frequency spectrum. So I'm going to give a general explanation of the spectrum, and little bit cover some topics, some properties here and there, and before we get on to actual useful useful spectrum studies. So this is going to be general, and I'm going to cover the entire spectrum. Okay, now see the frequency start from the lowest range. You just imagine we are increasing to the highest range. So as you can see, the lowest range here in this picture, it starts with 3 kilohertz. So the spectrum, if I were to explain, it starts at around approximately this frequency 3 kilohertz or so. They are all called the radio waves, and this spectrum is what we are going to study in our future. Now for this class, I will go a little bit ahead, and I will cover the salient features of the spectrum, which is beyond the radio waves, so that we have a general understanding. Now when we get to beyond radio waves, then we come across something called the infrared band, and then further, when the frequency increases, it is a visible light band, and further when we go beyond light, it is called the ultraviolet, and further beyond ultraviolet is the X-rays, and followed by gamma rays, and last at the end of the spectrum is the cosmic rays. So I'm going to touch upon these things, these spectrum bands a little bit, cover some interesting facts, and so that we know. But the point, what we have to understand it, it's to start from the lowermost, starts with radio, then it follows infrared, light, ultraviolet, X-rays, gamma, and cosmic. They are all in homogeneous nature of wave propagation, etc. We analyze the spectrum, or I explain the spectrum with respect to frequency. Now, if you are to take the wavelength, obviously the wavelength will keep reducing, because the spectrum, the frequency keeps increasing. So here we have, I have shown some pictures, and just to give you an approximate idea of the wavelength of that particular band. Now start with the leftmost of the radio wave spectrum, and keep going towards the right, and I have shown the figures of the expected wavelength. Now as you can see, the tower, the buildings, 10 to the power 2 meters, that's of the order of 100 meters. That's where our general radio waves are have the wavelength because of their frequency. And as we keep going further to the right, and slowly the wavelength keeps reducing, and within the radio waves, the wavelength is of the order of a human being's height, that's about 1.5 meters, so 1.25 meters, and thereafter further to a size of the butterfly, 3 to 4, 5 centimeters. And then when it comes to infrared, it's of the order of an eye of a needle, that is just about 10 to the power tip of the needle, that is 10 to the power minus 5 meters. If we move further right, it keeps reducing, and when we come to gamma rays, then The wavelength is of the order of a nucleus. That's what we need to you need to understand. I'm going to touch upon the salient and interesting feature of each band a little bit so that you get an idea, and thereafter we will be done with, because we are going to be concentrating on the other bands. First is infrared band. It's an invisible radiant energy, and we all learned about this infrared and how the body is able to absorb heat and then radiate heat, and the wavelength is of the order of approximately 700 nanometers. There are industrial, scientific, and medical applications, and we all know that the military applications include the target acquisition by night, and night vision, and homing, and tracking, etc. And other commercial applications include thermal efficiency analysis, environmental monitoring, industrial facility inspections, remote sensing, and wireless communication, spectrography, etc. And of course, you are all familiar with, or you are going to be frequently exposed to, the infrared weather of the satellite picture, which gives a different analysis of the existing weather. Okay, let's move a little bit further to the right, and now next band is the visible spectrum, that is the visible light spectrum. The wavelength is of the order of 390 to 700 nanometers, and it corresponds to a band in the vicinity of 430 tetrahertz. Now, we are all familiar with this Vibgyor, and we learnt how the rainbow colors are called the Vibgyor. As the frequency is increasing, it's actually in the opposite sense. That is, it starts with red and ends with violet. And this, of course, was coined by Newton, but subsequently there have been different thoughts, and sometimes some of the studies say that this indigo color actually doesn't exist, and it's a combination of two different colors, etc., etc. Anyway, as far as we are concerned, this we need, let's say that from the as the frequency increases, it the color ranges from red to violet. And of course, you are all very familiar with the prism experiments in your high school, and so that is a very proving phenomena, or the proving experiment of this particular visible spectrum. There's lots of other interesting facts which you could go through in your other from your other books. Okay, while I was preparing for this particular lesson, I found this particular information in the Wikipedia. How each color corresponds to a particular band of wavelength and the frequency, and there is an energy level of this. And somewhere I read, it is interesting to note that there are some scientists who related this to the seven notes of the octave, and they tried to conduct research how this particular band and the musical notes are correlated, if at all there was any. So I thought I must just make a mention of this. Those of you who want to know more about the subject, there is other material available in the Wikipedia. You can go through them and get enlightened. That we are the visible spectrum, it is important, I thought. There is a scientist, and they came out with the theory, young Helmholtz theory, in the year of 1810. They talked about three types of photoreceptors in our eyes. That is, we all learned about rods and the cones of when we learnt about in the anatomy of the eye, right? So this cones. That's what we are referring to. There are three different types which are preferring different three bands of color, that is the blue, green, and red. And yellow light uses different proportions of red and green, but very little blue. And similarly, other colors have used different combination of colors, but basically it's a mix of these are the three basic colors on which even all our computer colors also, or the coding is on this RBG color coding. You all may have noticed in many color coding nomenclature. So this is I thought it is interesting. You should know. If we further move to the right, comes the ultraviolet, and we all keep hearing about that ultraviolet band and how it gets many of the rays are harmful, but the useful effects of ultraviolet are it helps in production of vitamin D, and it helps to regulate calcium metabolism and improves immunity and insulin secretion and controls blood pressure, etc. So there are some bands of the ultraviolet band is useful for good health of all of us. Effects of UV rays, all we are all very familiar. They may cause skin cancer. Sometimes it causes eye irritation, and long time exposure may cause eye damage, etc., etc. So, these are the bad effects of ultraviolet. But luckily, we know most of it gets absorbed in the ozone layer. Further move to the right, that is go a little bit increase the frequency, we come across the X-ray. And X-ray is once again is another spectrum which we all are exposed to right from beginning. So I just want to bring to your attention that the frequency is of the order of 30 petahertz. Uh, that's the kind of and the wavelength is 0.01 nanometers. Practical, useful, commercial applications of X-ray, radiographs, CT scans, industrial radiography. In fact, sometimes the aircrafts are being X-rayed. The airframe of the aircraft are being X-rayed for fractures. Uh, and of course, day-to-day airport security luggage scanners are also deploy X-rays scanners. Further to the right, with the increase in frequency, we come across something called the gamma rays, and I have taken some interesting facts of this particular band. I just want you to notice the wavelength is less than 10 picometers. That is of the order of, as we saw, of a nucleus of an atom. Not even the atom, nucleus of an atom. So these are all emitted by radium and etc. So that's about it for this particular lesson. Okay, on the Earth, where gamma rays can be produced is by naturally decaying radioisotopes. That means after a nuclear reaction, nuclear energy plants, these after having undergone the reaction, when it is dying down, then they can give rise to gamma radiations, and of course, the externally, terrestrial thunderstorms can produce brief pulses of gamma radiation, and these sometimes these can be intense, especially in the sporadic 11 years spot cycles, etc. So that's we need to be aware of the sources of gamma radiation. Further to the right is the cosmic radiation. Cosmic rays are immensely high energy radiation, and mainly originating outside the solar system. And earlier I used to think that I was used to be under the wrong impression that as pilots we are subject to cosmic radiation and they are harmful. But what I have done studies, and they have done lots of research, and they have found that even around the year, if you flew the maximum limits, the existing limits of 1,000 hours, you are not exceeding not more than one fourth of maximum permissible limits. So there is no particular danger of cosmic radiation exposure for all of us. That's the point I would emphasize here. But what it is being mentioned is practically this pregnant aircrew. They need to be cautious because their effect, either it's not studied in full or it could be harmful. That's the point which I want to you all to understand. If you are if pregnant air crew around the year, if you are going to fly, of course it's not practical to fly around the year, but nevertheless, if you are going to be flying high altitude over the poles where the chances of exposure are high, maybe there are some effects. But on for a day-to-day operation for a normal pilot, there is no harmful effects of cosmic radiation. Having covered the salient features of the entire frequency band, let me go back to the beginning and let us visit the radio waves, that is 3 kilohertz to 300 gigahertz band. This is the band which we use more frequently for several practical applications in the aviation, and we are going to be studying this particular band in great depth. So that's where I will leave this class, and next class onwards we are going to be talking about this particular band and its properties, etc., in much more detail. And you are going to we are going to learn lots of practical aids and applications which work in these particular bands, and why? Because of its propagation properties, and etc., etc. So that's it. We will visit this particular band from the next class onwards. Hope you found this class interesting, and please feel free to comment on the email ID given below. And this is not very important. This is just to make the class a little bit interesting. So we are not going to be studying too much about all this further bands. Now we are going to be concentrating on the radio, the band, EM, that is the band which I discussed about. So that's as far as this subject is concerned. So I look forward to you all going through my future lessons as we go on this particular subject. Thank you all for going through this lesson patiently.